Back in middle school, I was a huge fan of the Eragon book series by Christopher Paolini. The magic system was fantastically simple. In short, you say in a magic language what a spell does, you add energy to it, and it just works. Now, for you diehards out there, I understand that there's more intricacies to the magic system, but for the most part, and for all my intents and purposes, it's that shrimple. Now, for the half dozen of you who watch my videos on the regular, you may be wondering what mathematics I am driving at. And to that rhetorical question, I say buckle in, because I'm about to turn the autism up from 500 to 501. Hello, my name is Sawyer West, and today we will be discussing how to build a Turing machine in the Eragon magic system. Now, before you get all snap into a Slim Jim anxious, chug a glass of milk, take a shot of your preferred brand of non-alcoholic whiskey, and tell yourself, this is fine. So, I managed to fit all the Turing techno-jargon on one slide to maximize your distress. But sadly, I won't experience any schadenfreude, because explaining Turing machines only requires one slide. Jokes aside, please bear with me for the entire slide. A Turing machine, in short, has a memory, called a tape, which can modify via memory operations, listed on instructions called states. That is a lot to take in one sentence, but I promise this will make sense. Disclaimer, if this doesn't make sense, you cannot sue me for false advertising. Think of memory like the reel of an old movie, but instead of pictures, Turing states store ones and zeros. Furthermore, just as two movie reels may store different movies, two Turing tapes may store different sequences of ones and zeros. Take, for example, the initial state illustrated in the top right corner of the slide, like a green ladder. In the space between the rungs, which we call cells, we store a 1 or a 0. That red triangle below the highlighted box represents a pointer that the machine uses to select a cell in memory. Now look at this drawing of a dog I stuck in to hit up your dopamine receptors so you keep paying attention. Once the machine uses the pointer to select a cell in memory, the machine can read the number stored in the cell to a register, where a register is a cell separate from the tape. Can write a new number to the cell from a register. It can move the pointer forward or backwards in memory to a new cell, or it can just stop, and we take the entire tape as output. Traditionally, nerds say halt instead of stop. I think because they want it to sound cooler, but they don't sound cooler. And let's hit up those dopamine receptors again. Now, since we humans are a lazy bunch, we want this machine to operate without us having to manually execute each memory operation. Those pesky reads, writes, moves, and halts. So we provide the machine with instructions. Each instruction contains a sequence of these memory operations to execute, as well as the identification number of the next instruction to load. Take a moment to consider the example instruction depicted in the mid-right diagram. Altogether, when started, the machine loads and follows an initial instruction to execute a sequence of memory operations, and it loads the next instruction. The machine continues to load and execute instructions until one of the instructions tells the machine to halt. We did it, folks. We got through one slide about abstract state machines. I'm going to take a quick tea break. Tea time is over. Back to magic. Now, I'm sure all of you are biting at the bit to ask one burning question. Since magic spells in the system require only energy and an explanation of what the spell is supposed to do, then we can feed this explanation of a Turing machine into the spell and get back to downloading cars, right? No. Paolini's official Eragon website has a dictionary of magic words that have been used throughout the series. Many of these words are useful for smiting your enemies, but few are useful for constructing abstract state machines. It's as if Paolini took an economical approach to language by building only the language he needed for his story. Our game plan will be to build up with the existing language a new vocabulary that is strong enough to describe a Turing machine. For your ease of reading, I'll put the spell in a bullet list to the left and stick the words for the spell with definitions off to the right. We define new words by leveraging Palanini's definitions of let and be to say, let definition be a word. Since Palanini provided us with definitions for and not, we can derive other logical operations. I'm not going to bog down this video with these proofs, but if you are ever so inclined, you may pause the video to inspect both these proofs and their definition spells. If formal logic is your thing, of which last slide is an example, I implore you to watch both my introduction to proofwriting video and my in-depth formal logic video. You may have noticed, if you snuck a peek at the Magic Dictionary, Palanini never defined numbers. We need numbers, and to define numbers, we need a word for size. Sadly, there's also no word for size. The best definition I could contrive with such a limited vocabulary is let the size of n be the carry of all in n. This is, to say the least, unsatisfactory. Disclaimer: if this spell turns your head into a puddle of Pepto-Bismol due to my lackadaisical rigor, I am not to be held liable for your injury or your subsequently stained carpet. Moving on, we can take the size of empty to define 0 and the size of a goat for 1. Yes, I am using goats as a unit of magical measurement. Bite me. But first, hold on to something. I'm going to rapid fire some definitions at you which accumulate to the definition of a Turing tape. Increments increase by 1 and decrements reduce by 1. With increments and decrements, we can iteratively define positives, negatives, and integers. Booleans hold true or false. A register holds a Boolean, and a tape is where each integer is assigned a Boolean. Take a deep breath and tell yourself, this is fine. We don't have much more to go. The next rapid fire will accumulate to a state. The memory pointer is an index on the tape. Read means the register holds the Boolean at n in tape. Write, vice versa. Halt just stops, and move increments or decrements the memory pointer. States contain a sequence of memory or logical operations and a number by which the machine can load the next state. And finally, let a Turing machine be states run on tape. We did it! Time for the postscript. I feel obligated to add this slide due to the current dystopic regulatory status of AI. Artificial intelligence was not used to produce this video. That's right. I used my brain to figure out the solution. I used my brain to communicate the solution with my own words, and I used my brain to draw art to facilitate this communication. I do not consent to my work being used to train AI models, and I do not consent to my work being used to prompt AI models. Thank you for watching. Remember to like, subscribe, and leave a comment below.